So, hey everyone, this is Nikhil Kilari and I am from fourth year, final year electrical engineering. The paper which we will be discussing today is called Scale, Space and Edge Detection using Anisotropic Diffusion, and the authors are Pedro Perona and Jitendra Malik. So this is the paper, this is the actual paper which we will be discussing. It's published on 7 July 1990. A basic intro about the authors. Pedro Perona is from Italy and he has done his PhD from University of California, and Jitendra Malik. He's an alumnus of IIT Kanpur. I also noticed an interesting part that, yeah, this guy, Pedro Perona, he has PhD from the Department of Electrical Engineering and also computer science. Crazy. So with the intro of the authors done, as the title suggests, it's called Scale, Space and Edge Detection using Anisotropic Diffusion. What exactly is scale space? Scale space here means time, and we'll be discussing more about this. And edge detection, as we know, as in our course, we have learned some edge detection methods, but this will be using anisotropic diffusion. Now, what is diffusion? So diffusion here means a type of blurring. As we know, we have used Gaussian blurring, which is a descendant of heat equation. And don't worry if all this terminology is confusing you, we'll be going through each and every step of this. Anisotropic diffusion means we blur the image anisotropically. Isotropic means equally dispersed in all the directions. But anisotropic diffusion here means we blur the image only inside its region, means we blur the image within the objects and we don't blur at the edges of the objects. So this makes edge detection much more easy and the final image looks feasible. So we'll be talking about or discussing about scale, space and edge detection using anisotropic diffusion. And this is the diffusion equation or the heat equation. After converting the heat equation into the image processing terms, we get IT equal to delta I. This is not intensity of a pixel at a time frame. IT here means derivative of intensity with respect to time. So that in discrete domain is nothing but delta I. And diffusion equation states that this is equal to Ixx plus Iyy. Now don't worry, I'll be telling or giving you about a brief intuition about this. Now what the diffusion equation states is that with respect to time, the intensity of the pixel should change in such a way that it should be equally dispersed in all the directions. Like Ixx here means dou square I by dou x square, and Iyy here means dou square y by dou y square. So in the whole, it's telling about the change in Ix. It's not simply exactly the change in Ix, it's the change in the gradient of Ix. Yeah, so It is equal to the change in the gradient of I in x direction plus change in the gradient of y with respect to time. As the intensity changes, it should be equally changing in both the x and y directions. And changing this into discrete domain, we get it plus 1. Now this is not derivative. This is it plus 1, means intensity of the pixel at time t plus 1, and this is intensity of the pixel at time t. I'm sorry I used subscript, it should not be subscript. So it plus 1 equal to it plus Ixx plus Iyy. Now how did this come? This is nothing but we just expanded delta I. And what is this heat equation doing in computer vision? So as we know, as we have already discussed, it's the pixel intensities are analogous to the heat. And as the time progresses, the pixel intensities are uniformly distributed, meaning the resolution becomes coarse and that image gets smooth. Another important outcome of this diffusion equation is the Gaussian equation, means g, x, y, t exactly satisfies this equation. So the Gaussian kernel is a solution of heat equation. So all the blurring which we have done till now is derived from this heat equation. So let's go back, let's clarify this again. So what this means is after expanding the heat equation, we get IT plus 1 equal to IT plus IXX plus IYY. So after iteratively applying this to each and every pixel in the image, what you get is Gaussian blurring. So that's cool. That's one of the cool things that I have learned by reading through this paper. And as the time progresses, the image changes as if a Gaussian kernel is being applied. So yeah, motivation of diffusion equation. So there are mainly two main motivations for this diffusion equation. So the motivations why the scientists have come up with this diffusion equation. It's because one thing is causality. A feature identified at coarse level. Now coarse level here means after a few iterations in time, means we take an image, we apply the above diffusion equation, that is this equation, multiple times, we get a coarser level of resolution. So that's what coarse means here. So a feature identified at coarse level of resolution should possess a cause at a finer level of resolution, although the reverse need not be true. Now what does this mean? So this means that if we take any pixel in the coarser level of resolution, which means after applying this after applying this equation multiple times to the image, and after getting the pixel intensities, each and every pixel intensities should possess some significance. But having a cause at finer level of resolution need not be present in coarse level of resolution, which means if at a finer level of resolutions, means in the past, if there is any cause that need not be present in the future, but anything present in the future should contain a cause, means it should have some significance for us. So that is what causality means. And homogeneity and isotropy. Homogeneity and isotropy means blurring is required to be space invariant. Now pay attention to this point. This is the point which is going to be controversial and will be directly hit upon by the paper Perona Malik. And here the scientist said that blurring needs to be space invariant. So it should be noted that the second criterion is only stated for the sake of simplicity. So the scientist wanted to keep it simple. That's the explanation that the paper has given. So in fact, the major theme of this paper is to replace this criterion with something more useful. So yeah, let's discuss about the weakness of standard scale space paradigm. Now what is the weakness over here? Now we have a tree with sky in its background. Now when we apply a Gaussian blur to this image, it blurs within the tree, that's good. It blurs within the sky, that's good. But it also blurs the sky, the region between the sky and the leaves, the edges. Now that is a problem over here. We don't want the edges to be blurred. And we also want, if there is any image like this, now if we apply a Gaussian blur to this image, now what happens is we lose the inner information of the leaf. Now that's a problem. We do not want to lose the inner information of the leaf. So yeah. Now and also there are three levels if we take basically any image of a tree. One, the finest level, and the medium level, and the higher level. When we apply Gaussian blurring, it's like losing both these informations, and we don't want to lose that information. And yeah, what are the drawbacks? The location of the edges are shifted from their true locations, destroying the most important feature required for edge detection. Now, when we apply a Gaussian blurring to an image, now what happens is we lose the edge information. We completely lose the edge information because as we can see, and the actual location of the edges are also shifted. It's like this edge region is shifted among all these regions, and we don't want that to happen. And Gaussian blurring does not respect natural boundaries of objects. And region boundaries are quite diffused instead of being sharp. That's what it means. The edges are not sharp in coarse levels. Coarse levels meaning in the future time. And this provides the new motivation. Apart from the causality being the same, there are two new motivation now required. The first one is the immediate localization, and the second one, piecewise smoothing. Immediate localization means at each resolution, the region boundary should be sharp and coincide with the semantically meaningful boundaries at that resolution. Now, at each resolution here means at each time frame, as we keep on iteratively apply the equation, we want the region boundary should be sharp and coincide with the semantically meaningful boundaries at that resolution. And piecewise smoothing. Intra-region smoothing should occur preferentially over inter-region smoothing. Now we don't want the region, inter-region to be smooth. Inter-region here means the edges. We don't want the edges to be smooth. Instead, we want intra-region smoothing. Means if there is an image like this, we don't want this region to be blurred, but we want the region within the rock and the mountains and the sky to be blurred. And that's what the anisotropic diffusion equation provides. Now consider the anisotropic diffusion equation. IT, now this is the derivative. IT is equal to divergence of C into gradient of I. Now this expands as C into Laplacian of I plus gradient of C dot gradient of I. Now if C equal to 1, let's assume C equal to 1. Now what happens? This will be 0 and this will become 1. I of t is equal to Laplacian of I. This is nothing but the heat equation. So anisotropic diffusion assumes C is equal to 1. And if C equal to 1, it means it is applying isotropically to each and every pixel. Now, what magic does this C do to make sure that the smoothing doesn't happen near the edges? Suppose that at the time scale t, we knew the locations of the region boundaries appropriate for that scale. We would prefer smoothing within the region in preference to smoothing across the boundaries. Yeah, that's true. And this would be achieved by setting the conduction coefficient to be 1 in the interior of the each region and 0 at the boundaries. Now what this means is that if we know the edges in a time frame, what we can do is make C equal to 1 inside the region and smooth that region, and C equal to 0 at the edges and leave that region. Now what he wants to do, what the anisotropic diffusion wants to achieve is make this C equal to 1 inside the region, means in the intra-region, and C equal to 0 at the edges. So that's what this means. And the blurring would then take place separately in each region with no interaction between the regions. That is the main task, means it is the main goal that we need. And the region boundaries would remain sharp. So this is the significance of C. But we still didn't discuss how we control this C, because one thing here is we don't know where the edge is. We just have the image. If we know where the edge is, then we can change this C equal to 0 at near the edge and remove blurring. We can make sure that it doesn't blur that region out. But we don't know that region. That's the main thing which we want to address. We still didn't discuss what is the significance of this C. As we have previously discussed over here, if we can control this C near the edges in such a way that it becomes 0, then it doesn't blur the edge out. But the main important thing over here is if we already know where that edge is, then we don't need this equation at all. But instead, we need a proper estimate of this C near an edge. Now that's a challenging task. Let's see how this is. What can be computed here is a current best estimate of the location of the boundary edges appropriate to that scale. Now scale here again means time. Don't get confused. Scale sometimes scale means that enlarged or something out, but that's not the case over here. Scale here means time. Now what we want is a current best estimate of the location of the edge. If we know an estimated region of the edge, then the gradient in itself is an excellent estimate of the location of an edge. If the gradient is high, that means there is probably an edge over there, and we can stop our blurring at that region. So that exactly is what is being proposed by this paper. Now C is nothing but a function g which is being applied on this gradient of I. Remember this carefully. C is equal to g of gradient of I. A simple exponential function does the work for us. E power minus norm of gradient by k square. Now we can control the constant k as we want, but what is the catch over here is if the gradient of intensity is very high, it makes the function g is equal to 0. And if the gradient is small, it makes equal to 1. Now we have achieved what we want. All we need to do is think how we achieved this. We have an image, and in this image, if we are at this pixel, after converting this into a black and white pixel, of course, now the gradient here is very small, which means we are within a region of an object called water over here, and we need to blur this pixel. Whereas if we are at this pixel, the gradient is very high in this direction. So it means we don't want to blur this region. So we are at an edge and we don't want to blur that edge. So G gives an excellent approximate for this. So if the gradient is high, then G becomes close to 0. Otherwise G becomes 1. So another alternate function for this is G of gradient of I is equal to 1 by 1 plus norm I by k square. Again, if norm is high, it makes G equal to 0, or norm is less, it makes 1 by 1, which is equal to 1. So these both equations work in the similar fashion. All the information that we have, and we need to apply it on an image. And how do we apply it on an image? And let's assume this is the pixel. This is the center pixel which we are at, I of I comma j. And we take 4 directions: north, east, south, and west of the pixel. And we take the gradient in this direction and in this direction, in south and in west. And after computing gradient in all the 4 directions, we apply C on the gradient in each direction. Means Cn. Cn here means G of gradient of In, and Ce means C of G of gradient of IE. So after computing the gradient, we apply C to it. So now we have all the gradients, and we know if the gradient in a direction is very high, then C becomes 0. So it means it restricts the blurring over there. But we still don't have a complete equation for this, and here it is. Now as we can see, as we can go here and see the anisotropic diffusion, IT means derivative of I is equal to C into Laplacian of I. And now here we approximate this thing. We neglect this thing because product of two small values means it's negligible. And after expanding this, we come up with this. I of t plus 1 is equal to it. Now t plus 1 is a time. I of I at time t plus 1 is equal to I at time t plus lambda times. Let's see why this lambda is introduced over here. Now we compute the gradient in all the directions, north, south, east and west. After finding the gradients, we apply C in each gradient, and after applying C, we multiply this both. Now what happens after multiplying this both? If the gradient in north direction is very high, we make that to close to 0 by multiplying it with C. If the gradient in south is very high, we make it near to 0 by multiplying with CS. And if the gradient is high in any region, in any direction, then we make it close to 0 by multiplying it with C. And we add this complete change by multiplying it with a scale factor called lambda and add it to the present intensity pixel value. Now what happens after iteratively applying this equation? Just imagine we have 2 pixels and 1 pixel is higher in value than the deciding pixel. Now let's assume this is the pixel. This value is small and this value is high. Since the value of this is small, what happens? The gradient in this direction will be less, the gradient in this direction will be less, and the gradient in this direction will be less, and the gradient in this direction will be very high. So this contribution becomes 0, but we still have 3 directions contributing. Because 3 directions are contributing, we add the appropriate value to this, which whatever we get from here, and after adding to that to the current pixel, its intensity's value will increase. And if it keeps on, but remember, here the intensity value is very high, so all the contributions will become zero, probably because here it is very less and less again, which means this is an outlier. Let's assume this is an outlier with small values over here around surrounding this, but this value is less. So since the gradient is less, we are keeping on adding iteratively to this. Now what happens? This value increases approximately equal to the value at this pixel. So when the two pixels are nearby, that's what we mean, calling it as blurring. So let's take the brain image. Now what happens? We can see there's a lot of noise. To get the edges from this image, what do? We normally apply a Gaussian filter or Gaussian kernel, sorry, to smooth the image. If we apply Gaussian kernel over here, it becomes too blurry. It becomes too blurry and we lose all the inside edges. But after applying anisotropic diffusion, see what happened. We got even the finest details inside your image. And this here is a pattern, and we, after applying Gaussian blur, this is what we achieved. But after applying anisotropic diffusion, we can see the edges sharply concentrated. And that concludes the slides. So yeah, thank you. So in the whole, all to summarize each and every aspect that we have learned here, we first started with a normal heat equation. We saw what are the weaknesses of it, and we saw what are the drawbacks of it. And after introducing two new criterion, we saw how they changed the diffusion equation. And after the change, and after introducing a new function called z and applying it on the gradient, we were able to see if it is an edge or not. And by applying the diffusion equation, an isotropic diffusion equation, iteratively, we get what is called anisotropic diffusion. So yeah, this concludes the presentation. Thank you. Please let me know if you have any doubts in the comments. Goodbye. Peace.